into transitions to is ground state with n+1, correct? Okay. Corresponding to the atom having emitted the photon. Right? So if I were confined to, all the dynamics would be confined to these two states. Right? So I could expand the state, any state, in terms of these two states. And let me write, so I feel the T should be expanded in terms of, because this is the excited state, this is the ground state. So let me write C, E, N of T. Let's not even worry about that. Times E, T plus C. Sorry. Right? Okay. So now what are we doing? Essentially, we're back to doing two-level quantum mechanics, except that these two levels now are written in direct product space. And that's okay, because this interaction Hamiltonian, the operators are also written in direct product space, and then we'll just seek the things that they operate on. So if I were to basically, I plug this into here, okay, I turn this equation into a component equation, okay, and it's actually very simple. Think about it. So the IH bar, the time derivative, which I denote by a dot, this is going to be contributed from this term, right? Okay, this term while being operated on by this, annihilate a photon, turns n+1 to the n state, and then raise the atom. So this is like Cg of T. Obviously, you need to attach that. When you when you annihilate the photon, what happens? You get an n+1 factor, right? And of course, you pick up the lambda things, right? Okay. And then you get, when you raise the atom, nothing happens. Just E and N. So, and then the E and N thing cancels on both sides. So you match the component and it goes like this. For the other one, you get something similar. Cg dot of T. This one, you go from here. Lower the atom, no factors, right? And then you raise the n. When you raise the n again, you get a square root of n+1 factor. So you get lambda Ce square root of n+1. So obviously, these two coupled equations have a simple solution. It's just cosinusoidal or sinusoidal, and the frequency is just lambda n+1 times t. So basically, given the initial condition that given this at time t equals to 0, I get that C E of t is equal to cosine lambda squared and C2 of minus. Okay, so this is a simple solution in the simplest case possible, where we have the exact resonance and initial condition was the atom in the excited state. Okay, so notice something interesting here. Okay. Even if we started with no atom, no photon even if we started with no photon at all in the cavity, okay, you still get time evolution, right? Okay, you just get lambda t. And the time evolution depends only on how much the atom is coupled to the field in the cavity. This is called, so what's happening? The atom is essentially giving off a photon, reabsorbing it, giving off a photon, reabsorbing it. Okay? And the frequency that this happens depends on how much the atom is coupled to it. So essentially by coupling the atom, by engineering the coupling constant between the atom and the field, you can control how the atom spontaneously emit the photon. this is engineering spontaneous emission. Okay, so this also has the name of Rabi oscillation, fractal Rabi oscillation. Okay, and we can talk about this starting on Thursday. All right. So, are there any questions? I guess if not, then let's go.